Hello everyone, my name is Khloud and I'm a computer engineering graduate from Qatar. In today's presentation, we will discuss the findings of our drone detection research, which was done during our senior project year in university. We have conducted a study to explore different object detection algorithms on multiple publicly available drones datasets to evaluate their performance. The study can be used as a reference to those who are interested in this topic. Moreover, we are also proposing a new dataset. In this presentation, I will walk you through the introduction, and then we will move on to the related work where we will discuss the state-of-art literature related to the drone detection and drone classification. After that, we will discuss our proposed methodology, and then we will be sharing our results. And finally, we will wrap up the findings in the conclusion. We hope that after this presentation, you will have a better understanding of this topic. As the technology evolves, the drone market is rapidly growing. Many people use this technology of aerial vehicles to help them accomplish their daily tasks. Drones are used in different sectors such as videography, search and rescue, agriculture, and transportation. However, the drone advanced technology can be misused by malicious entities in many different countries by adding payloads like drugs or even bombs. Such manipulation can affect the safety of highly sensitive areas such as the military bases, airports, or extremely crowded areas. As it's shown here, this is all the drone incidents documented by press worldwide affecting different industries as airports, prisons, or even stadiums. Therefore, it's very important to have a robust detection mechanism. After reading a lot of scientific papers related to drone detection and studying the used algorithms and datasets, we have considered using different versions of the famous YOLO algorithm, along with Detectron version 2, since it's a real-time object detection that is used in video surveillance. As shown here in the table, there are 3 open source drone datasets that were considered during this study. The first dataset consisted of 1,359 images of drones as well as some noise images. The drone type in this dataset was not specified and the dataset had multiple types of drone. The second dataset consisted of 4,000 images of drones and some noise images that included drone-like images and non-drone images. The drone type in this dataset was not specified. The dataset had multiple types of drones. Moving to the third dataset. In the third dataset, it contained 2 types of videos, the infrared videos as D3A and visible videos as D3B. This dataset had 4 classes: airplane, birds, drones, and helicopters. In the drone class, there were 3 different types of drones. The total number of the annotated videos was 650. We have extracted the videos into images with their annotation. The format of the annotation and the content were manipulated mathematically. It's worth to mention that the above dataset have limitations as limited number of drones type and the ratio of each drone type is not specified. In our proposed dataset, we have addressed the limitations. We have increased the number of drones type up to 7 types, and the ratio of each drone type is specified as per class. The dataset consisted of 2,975 images with 7 types of drone from each class. The drone types were chosen based on the available drones, and some of the images were extracted from YouTube videos. The drone classes are Bebop, DJ Phantom 3, DJ Phantom 4 Pro, Emax, Intel Aero RTF, Mambo, and YH19HW. As shown here, the Bebop class consisted of 487 images. The DJ Phantom 3 class has 166 images, and the DJ Phantom 4 Pro class has 659 images, and the Emax has 334 images, and Intel Aero RTF has 256 images. In Mambo class, the number of images was 591, and the last class we have 482 images. For dataset split, all the datasets followed the same split of sets: 70% as training, 10% as validation, and 20% as testing. However, since the second open source dataset came with some unannotated images, we considered using 70% training set, which included 10% validation, and the remaining 30% were used as a testing set. In this research, we have considered 4 real-time object detection algorithms: YOLO v3, YOLO v4, YOLO v5, and Detectron 2, to evaluate their performance across 3 open source datasets and our proposed dataset. For training the model, we have considered using Google Colab, which provides access to powerful computing resources, including free GPUs. RoboFlow has been used to annotate the images. The useful tool offers an automated data annotation. However, some images needed a manual annotation. In the evaluating the models, we have used the following matrices: the mean average precision, which measures the agreement between the model's predicted bounding boxes and the ground truth annotation; precision, which quantifies the accuracy of positive predictions made by the model; recall, that measures the model's capability to capture all relevant objects in the image; finally, F1 score, which provides a balanced measure of the model's performance considering both false positive and false negatives. In the evaluation part, we will be discussing the evaluation of the open source dataset first. It's worth noting that some of the algorithms were eliminated due to the low performance results. Also, we have tried to avoid overfitting by fine-tuning the parameters of the algorithms, which included decreasing the number of iterations and increasing the number of the images. As shown here in the table, the first dataset we used YOLO v4, YOLO v5, and Detectron v2. The highest mean average precision was Detectron v2, scoring 96.672. Comparing the results to the result obtained from the original paper, we can see that all the algorithms that has been used in this study showed better results than the tiny YOLO v3, which was used in the original paper. For the second dataset, we have applied all the 4 deep learning models, and as shown here, the YOLO v4 scored the highest mean average precision, which was 93.57. Also, we can see that the lowest score was 84.6, which belongs to Detectron v2. Moving to the third dataset, both A and B, in the original research, the authors used YOLO v2, and the score was 70.97 for D3A. However, we were able to get better results for the same dataset, scoring 99.49 using YOLO v5. Also, in D3B, the highest mean average precision was also scored by YOLO v5, achieving 95.36. As shown here, all the algorithm that has been used in this study showed better result than the original paper's results. On the other hand, for our proposed dataset, we have applied the 4 deep learning models, and the highest evaluation was achieved by YOLO v3, scoring 99.58, followed by YOLO v5, 85.3, and the lowest score was achieved by YOLO v4 at 73.94. Also, we have trained the model for each class to explore the results. Overall, YOLO v3 scored the highest mean average precision. In addition, we would like to announce that our dataset is available via Google Drive link in the reference list of the paper, which includes the images along with their annotation. Moving on to the results, as we can see here, this is the result of the deep learning models on the first dataset. Along with that, we have also included the mean average precision graph of YOLO v4. Next, we have the different results of the graph on dataset 2. As we can see here, the model were able to detect and also classify the drones. Also, we have included some of the performance graphs of YOLO v3 and YOLO v5. Moving on to the last dataset, we can see here that the models were able to classify both datasets. Lastly, here are the results of our proposed dataset. To conclude this presentation, I would like to summarize the findings and point out the highest score algorithm for each dataset. For the first dataset, the highest score was achieved by Detectron v2, and for the second dataset, YOLO v4 performed better than the rest of the models. YOLO v5 showed better results not only in our proposed dataset as well as dataset 3, both A and B. Also, I would like to mention that we have learned a lot of new things while conducting this study, and we were introduced to totally new field. And we have done our best to achieve the aim of this research. And for future, we would like to increase the number of classes in the dataset in a way that includes more various types of drones and introduce some noise to the data. I would like to thank everyone for your attention, and we may proceed with the questions.